Hi everybody, I'm Martina Lippi from Roma Tre University, and today I'm going to introduce you our work about a finite-time distributed protocol for link prediction in networked multi-agent systems. And this work was done in collaboration with Matteo Santilli, Gabriele Oliva and Andrea Gasparri. The motivation behind our work is that complex networks allow to model a wide variety of social, technological, and biological phenomena. However, due to the high dimension of these networks, it is often impossible to quantify the degree of interaction among all the nodes of the network. And therefore, it is extremely important to have the ability to assess the strength of the coupling between pairs of nodes only on the basis of a sample of known interactions. And this problem is generally known as link prediction problem. In this context, existing approaches are typically either centralized or they rely on a complete interformation setting, while in this work we propose a distributed protocol for link prediction which guarantees finite time convergence. And for this purpose, we build on the framework by Petch et al., which considered a complete network topology and a centralized architecture, and we move to the case of sparse graphs and distributed computation. So in order to derive the distributed protocol, we first need to model the network. And given a network of n agents, we model all their potential interactions by a directed interaction graph Gi, in which each vertex represents an agent I, while each edge ij encodes the strength of interaction Wij from agent I to agent j. We introduce also the adjacency matrix W, which possesses entries Wij if the edge ij exists and zero otherwise. And as mentioned before, we assume that only a subset of the interaction weights is actually known, and we denote the graph of the observed or known interaction as GOI. And similarly to the interaction graph, we introduce the adjacency matrix of this graph A, whose entries are equal to Wij if the interaction ij is known and are zero otherwise. And finally, we introduce the undirected version of GI, which models the communication between the agents and is referred to as communication graph GC. We also made the following assumptions in the work, which are that first we assume, as in Petch et al., that all the interaction weights Wij can be represented as linear combinations of the known weights and suitable terms Zij, which represent the contribution from agent I to agent j. Moreover, we assume that in the incomplete information setting, the contributions Zij are zero whenever the interaction from I to j does not exist. So based on these assumptions, we can define the likelihood Sij of existence of a link Ij as a linear combination of the known weights Aik and the contributions Zkj. And this relation can be written in a compact form as S equal to Az. So at this point, we are ready to formally state the main problem addressed in this work, that is, given a multi-agent system with n agents and interaction graph Gi, our objective is to define a finite-time distributed protocol which allows to collectively select the optimal Z star obtained by minimizing the cost function in equation 2, where alpha is a scalar value between 0 and 1. So in other words, our objective is that each agent I with n state variables Zij converges to the optimal state values Z star Ij in finite time. And here, the rationale behind this cost function f is that we try to maximize the similarity between the known weights A and the likelihood matrix S, and we also minimize the norm of Z in order to avoid overfitting. So in order to derive a solution for this problem, we first characterize the structure of the optimal solution, and then based on the derived condition, we define a distributed protocol. So regarding the optimal solution characterization, we have that the unique optimal solution Z star satisfies the optimality condition in 3, and this is obtained by imposing zero derivatives of the cost function f and by properly rewriting the cost function and computing the derivative. In particular, this leads to the following compact form in equation 6, which can be rewritten as in the theorem. Regarding the uniqueness of the solution, this follows by proving that the cost function is strictly convex. So given this optimality condition, we also introduce the vectorized version, which is useful for our distributed protocol. In particular, we introduce the variables eta, which is the vectorization of Z, H, which is the vectorization of the optimality condition G, and then we have the matrices D and Q, where Q is symmetric and positive definite. So based on these variables, we know that the vectorized solution eta star satisfies the condition H of eta star equal to the 0 vector. So at this point, and based on this optimality condition, we can derive the distributed protocol by solving a zero-finding distributed problem. In particular, we propose the following control protocol in which each agent I runs a different update law depending on whether the agent J belongs to its one-hop neighborhood or not. And here, we can also notice that this equation requires the two-hop state information, which, however, can be estimated with a one-hop finite-time observer proposed by Gaspari and Marino. So in order to prove the theoretical convergence of this distributed protocol, we also introduced the stacked vector of the update laws, and we obtained this collective dynamics in which the derivative of H with respect to eta can be is equal to dqd, which is symmetric by construction and has minimum non-zero eigenvalue greater than or equal to 1 minus alpha. So at this point, we can formally state our main theorem, that is, given a multi-agent system with the dynamics in 10 and with positive gains, then there exists a finite time t such that the vector h converges to 0 in finite time, and t is upper bounded by a positive finite value t max dependent on the gain gamma, the parameter alpha, and the initial optimality condition h. In order to prove this result, we can consider the following generalized Lyapunov function, which is 0 in the 0 vector and is positive when the optimality condition is not satisfied. And here we can also notice that by virtue of theorem 1, when the optimality condition is satisfied for a certain eta, then this also implies that the eta is equal to the optimal eta star. So by resorting to the no-smooth Lyapunov theory, we can compute the generalized time derivative, and in this case the generalized gradient has the following structure in 15, where the bold sign represents the set valued sign function. And here we have that a generic vector xi belonging to the generalized gradient can be expressed as in 16. At this point, by noticing that the proposed control law is the non-smooth version of the gradient descent flow of a differentiable function, we can derive the inequality in 17, where the matrix M is equal to dQd. And by exploiting the knowledge of the structure of the kernel of M transpose M and the properties of the matrix D, we can ensure that as long as the optimality condition is not verified, the generalized time derivative is negative. In particular, we have the upper bound in equation 18, which guarantees that H reaches the origin in finite time. At this point, by integrating the generalized time derivative of the Lyapunov function, we obtain the relation in 19, which finally leads to the upper bound Tmax in the theorem. So we also validated the approach with numerical results and with potential-based interaction graphs composed of 15 agents. And here on the left we have the evolution of the state error norm, while on the right we have the optimality condition norm, and we observe that all the variables converge to the origin in finite time. We also compared the approach denoted by LO with other existing approaches in terms of prediction error, and we have that for all the graph sparsity coefficients, our method outperforms the others. So in conclusion, we proposed a link prediction framework which builds on the framework by Petz et al. And for this purpose, we first derived the optimality condition of the unique optimal solution, and then we define a finite time distributed protocol, and we validated the approach with numerical simulations. As future work, we want to extend the approach to constrain the time-varying interactions and to mitigate the multi-op requirements. So thanks a lot for the attention, and if you have any questions, just email me.